My name is Alden Connor. I am a research application manager at the Alan Turing Institute. So I work with projects across the ENS Grand Challenge to help them think about real-world applications of their work. And today we're going to do a series. We're going to start with a series of 3 short talks on societally relevant applications. Our first speaker will be Isabelle Tingzon from UNICEF. She'll be joining us virtually, followed by Paul Harris from Rothamsted, also joining us virtually. And then we've got Arjun Biswas, who is here from the University of Exeter, and he'll be joining us on stage in person. So we're going to have each speaker present their individual talks, and then we'll have a joint Q&A. So please put your questions in the Slido. And then at the end, we will also have a mic in the room, but all the Q&A will be reserved for the end. So we will go ahead and start with Isabelle, and I believe she should be joining us via shared screen, although I am not in charge of the tech. There we go.
All right, so I hope everyone can hear me. So good afternoon, everyone. It's a pleasure to be here virtually at Climate Informatics. Today, I'll be presenting our work at the World Bank under the Global Facility for Disaster Reduction and Recovery, or GFDRR. So our work is entitled Mapping Housing Stock Characteristics from Drone Images for Climate Resilience in the Caribbean. So just a bit of background, as some of you might know, the Caribbean is among the most climate vulnerable regions in the world due to the prevalence and intensity of extreme climatic hazards, such as tropical storms, floods, and landslides. In recent years, Category 5 hurricanes have devastated many small island developing states, with the highest degree of losses often sustained in the housing sector. So for example, in 2017, Hurricane Maria damaged or destroyed over 28,000 homes. That's about roughly 90% of Dominica's housing stock, accumulating costs upwards of $380 million in the housing sector alone. Now, this has spurred ambitious climate resilience programs by national government agencies. So, for example, the Disaster Vulnerability Reduction Program, or DVRP, by the government of St. Lucia seeks to reduce vulnerability to climate impacts through institutional strengthening of structural assets. Another example is the Resilient Housing Scheme by the government of Dominica, which strives to make 90% of Dominica's housing stock resilient by 2030. So in order for these climate resilience initiatives to be successful, local and national government agencies require reliable, complete, and up-to-date housing stock information to inform strategies for retrofitting and reconstruction efforts. However, because of the high costs and long timeframes associated with data collection, which is typically done through house-to-house surveys, housing stock data is often limited, incomplete, or even completely non-existent, especially in many small island developing states, thus prompting the need for alternative and more cost-efficient approaches. So in response to these challenges, we've turned to AI and Earth observation to help fill in critical exposure data gaps. So under the Digital Earth for Resilient Caribbean project, our goal is to enhance local capacity to leverage AI and Earth observation in support of resilient housing operations. So the project has 3 main components. The first is capacity building. So, for example, my team and I are working to establish GIS units within national government agencies and working to train and upskill government staff, community mappers, and disaster responders in the use of Earth observation data, geospatial services, and AI tools. Oh, sorry. We also provide support in terms of generating and integrating and using critical baseline exposure datasets derived using AI and Earth observation-based technologies. So this is operational support in the use of AI workflows. And finally, we facilitate knowledge sharing and dissemination by organizing conferences and workshops to promote our methods and tools and encourage wider adoption across the Caribbean region. So going back, the Digital Earth project essentially leverages several different Earth observation datasets. So this includes very high resolution aerial images, primarily in the form of drone images, but we also use orthophotos and LiDAR data, We also used building footprints data delineated from aerial images. And currently we are also exploring street view photos taken using GoPro cameras mounted on top of cars. So I'll be, in this presentation, I'll be discussing mostly the aerial images. So we used two types of very high resolution aerial images. So the first is nationwide orthophotos taken by attaching a camera to an aircraft and flying it across the whole countries of Dominica and St. Lucia, resulting in 10 to 20 centimeter per pixel resolution aerial images. And while this does give us complete coverage, it's unfortunately very costly and quite unsustainable to acquire frequently. And so moving forward, we look towards drone technologies to generate higher resolution aerial images, which range from 2 to 5 centimeter per pixel resolution. So it's definitely less scalable compared to orthophotos or satellite images, meaning it's unlikely that we'll be able to get nationwide coverage, but it does have the advantage of being much cheaper, allowing for more frequent data acquisition, which is, of course, critical in disaster contexts. So part of the project, for example, involves training local government staff to operate drones and coordinate pilots in order to acquire and obtain drone images on a more frequent basis. So next, we generated building footprints using aerial images. So we actually started by looking into publicly available building footprints from Microsoft, Google, and OpenStreetMap, but found significant misalignment between these publicly available building footprint polygons and the underlying drone images, as you see in the slide. And so we turned to segment anything model, or SAM, to delineate building instances directly from the drone images. So you might be familiar with SAM as a popular instance segmentation model, which can also be used to extract building polygons from aerial images. So more specifically, I used a variation of SAM called LangSAM, or language SAM, which combines the power of instance segmentation with text prompts to generate masks for specific objects within the image. So here I used the text prompt house to generate building footprints for every building in the image, and found that LangSAM generally worked well out of the box for our drone images. So given that we have the aerial images and the corresponding building footprints, we then proceeded to crop the image by getting the minimum bounding rectangle around each building footprint. And then we manually labeled around 14,000 buildings according to two categories. So we have roof type and roof material. So roof type basically includes or consists of flat rooftops, basically rooftops with slopes less than 7 degrees. We have gable, which is pitched on two sides up to a central ridge, and hip, which is pitched or sloped on 3 or more sides. We also have roof material, which consists of categories or classes such as concrete or cement, healthy metal, irregular metal, meaning metal rooftops with some form of rusting patches or some form of damage. We have blue tarpaulins. So in the context of post-disaster, in the post-disaster context, we find that many severely damaged rooftops are often covered in blue tarpaulins. And the last category here is incomplete, indicating that the rooftop is either under construction or severely damaged. So we show here the class distributions of roof type and roof material classes across Dominica and St. Lucia for the training and test sets. We note that the data for Dominica was collected using post-disaster aerial images in the aftermath of the Hurricane Maria in 2017. So meaning for Dominica, we see significantly more blue tarpaulins and incomplete buildings than in St. Lucia. So actually we see that in St. Lucia images which were taken more recently in 2022, these have fewer incomplete buildings and actually no blue tarpaulins. So we definitely see a difference in class distributions between Dominica and St. Lucia. And so using the 14,000 annotated buildings, we trained CNN models to predict roof type and roof material attributes using standard model development workflows, as you can see here. And so we summarize our end-to-end workflow as follows. So we start by taking the aerial images and running them through the segment anything model to generate building footprints. And then using the building footprints, we then crop the image using the minimum bounding box for each building footprint and run this through the trained CNN model to generate the roof attributes. So we show here the test set model performance of different CNN architectures for roof type and roof material classification, trained and tested. So we trained and tested using only the Dominica data set, and then we trained and tested using only the St. Lucia data set, and then finally we experimented with training a model using the combined data sets of Dominica and St. Lucia. So the performance scores that you're seeing here are the combined test set, are the results for the combined test sets from Dominica and St. Lucia. And so essentially, we show here that the local models, essentially models trained and tested within the same country. For local models, the EfficientNet and ResNet 50 architectures generally achieve the best F1 scores. Next, we evaluate explore the cross-country generalizability of the best local and combined models. Specifically, we seek to answer the questions, one, how well do models trained in Dominica perform for St. Lucia and vice versa? And also, how well does a model trained on the combination of Dominica and St. Lucia perform compared to models trained using only local data? So as you might expect, we observe performance degradation in the face of geographic distribution shift, meaning models trained in one country and tested in another country perform worse than models trained and tested within the same country. We also show that a model trained on the combination of Dominica and St. Lucia performs marginally better compared to models trained using only local data, and this is for roof type classification. However, for roof material classification, we find that locally trained models actually consistently outperform the combined model. And we posit that this is likely due to the shift in class distributions between Dominica and St. Lucia. So again, aerial images in Dominica were taken after Hurricane Maria in 2017, when many rooftops were damaged or destroyed, whereas aerial images for St. Lucia were taken more recently in 2022 in non-disaster contexts, meaning St. Lucia has fewer incomplete buildings and no blue tarpaulins. And so based on these results, we urge caution in applying locally trained models off the shelf to new geographic regions and emphasize the significance of collecting local and highly contextualized training data. So using our best models, we generated nationwide roof classification maps for Dominica and St. Lucia. We also applied our model to Grenada, but we have yet to evaluate the results as we're currently still in the process of collecting and annotating ground truth data for this country. So in this next slide, we show how with the frequent collection of drone images, you can use these tools to efficiently identify high-risk structures and rapidly assess building damage after disaster events. So for example, we show here the pre- and post-disaster roof classification maps in Dominica, Calihut, taken before and after Hurricane Maria in 2017. So you'll see that before the hurricane, a lot of buildings classified as a lot of the buildings were classified as either healthy or irregular metal, as you can see in the green and the red buildings, which then changed to incomplete or blue tarpaulins, as shown in purple and blue after the disaster event. Finally, our future / ongoing work includes using street view photos to capture building characteristics such as building material, occupancy type, completeness, security, etc. This is done by strapping GoPro cameras on top of cars and driving them around the neighborhood. So this work is done in collaboration with Development Seed, and we're working essentially on using building detection and classification models for street view photos, as you can see here. Lastly, I want to just underscore the importance of local capacity building and democratizing AI and Earth observation-based solutions. So specifically, I want to emphasize that a bottom-up approach that involves local communities in the collection and generation of critical housing stock information ensures sustained adoption of solutions that fit local needs and that build long-term capacity. So to summarize, we show that combining AI and Earth observation with local knowledge and expertise has immense potential to enable more timely, data-driven decision-making in support of resilient housing and infrastructure. We emphasize the importance of local capacity building, skills development, co-creation of geospatial data, and open source tools in the responsible and inclusive deployment of AI solutions for disaster reduction and recovery. And by using innovative technologies, governments can be better equipped to not only respond more immediately to post-disaster needs, but also anticipate and manage risks, thereby improving climate resilience in the region. So that ends my presentation. Thank you very much.
So we'll do questions at the end, and our next speaker is Paul Harris from Rothamsted, who's also joining us remotely.
Can you see my screen okay?
Yes.
Yep. Okay, then I'll go then. So just a quick summary of what I'm going to talk about. I'm going to a few slides on the challenges facing agriculture due to climate change. Then I'll describe an existing data platform that we're going to build a demonstrator digital twin on. This data platform has been in operation since 2010. So we've and it consists of 3 outdoor farms and 1 indoor farm, and we've collected an awful lot of data in the last 14 years. So it's ideal to act as a demonstrator digital twin. It's not going to be a real digital twin because it's not a real farm, it's an experimental farm. So I'll describe how we're going about that. We're just at the start of our journey, essentially, trying to build a digital twin at the farm scale. And then I'll finish by how we intend to roll the technologies out to real farms. Okay. So the challenge. So agriculture is both contributes and is impacted by climate change. Agriculture contributes primarily due to greenhouse gas emissions from livestock, but is also impacted by climate change, by extremes like extreme rainfall, extreme drought, and then so those are the challenges agriculture faces, and there's various solutions by on-farm mitigations and interventions. So it's a bit of a double whammy, really. Key concepts in agriculture are sustainable farming and resilient farming. Sustainable farming tends to sort of balance productivity and social aspects against trading off against environmental disbenefits and pollution and greenhouse gases. So we want sort of a bit of a balancing trade-off act, and the data and the models will reflect that. But farming also needs to be resilient, especially due to increasing abiotic and biotic stresses due to climate change. So here we want to see how we can see stresses in our farming systems and detect signs of collapse and critical slowing down, and possibly even tipping points, and possibly in soils and stuff. And then to inform these concepts, we need data, and that's sort of I'll describe the data platform that's currently in existence, so we can inform research on these aspects. So the data platform. So here's the data platform. It consists of 3 small outdoor farms and 1 indoor farm. It's been running since 2010. Periodically, say every 5 years, the systems change, so we can compare. It's all about comparing the systems, different systems, for their sustainability and or their resilience, and also increasingly net zero characteristics. So originally they were all permanent pasture. They're all livestock farms. And we've gone through, we're in the second system change period at the moment, where we've got one arable farm, 2 grassland farms, cattle and sheep, and also 1 housed indoor farm just for cattle. And next year we're going to transition another farm to a management land use that's currently undecided. So this data has been very useful for research. The data's always been open. That's part of the funding mandate. It's also used as an open facility where you can come and do a more campaign style experiment with a limited data collection that complements the core data collections that we make open. The map you see on the left-hand side there, you've got the location of the sensors, and it's far more than that map shows. I need to update that map essentially. So we're having far more soil moisture sensors, more biodiversity sensors, enhanced remote sensing ground reference, and more greenhouse gas sensors. So that's the platform, 4 farms. Here's the data collections in more detail. The ones in red are the data that goes straight to the cloud. There's over 80 million measurements so far since its operation. Remember, we didn't have all these collections from day one. Collections have appeared as we've got more capital investment. Currently got over 400 environmental sensors on the farm platform, measuring all the inputs and outputs as we possibly can for those 4 farming systems. So the core categories are farm management. So we've got all the farm management data, we've got crop performance data, got livestock performance data, water emissions. So that's the physics and the chemistry. In fact, the water emissions are the jewel in the crown. That's by far and away the biggest investment for the farm platform. We've got soil water data, met data, greenhouse gas emissions, field surveys, remote sensing from the forage harvester drone with various cameras on, and also, of course we get satellite data. But we'll always ensure that the ground reference for the remote sensing is good. And we've also got bioacoustics and biodiversity data sets. So all that data is made openly available and has been pretty successful in many research publications. So here's the data sort of pictorially. It's always nice to see it in nice pictures. So we've got the fixed data, the topography, soil class boundaries, farm management, weather data, soil physics, chemistry, also biology. We've got some limited livestock movement data. That's actually more campaign data. That's not currently open. And then emissions to air and to water. We've got livestock and crop performance. So remember, there's two livestock farms, 1 arable farm, and 1 indoor farm, and then also got biodiversity status. And even then, even though we were collecting an awful lot of data, it doesn't actually capture everything. So we can combine this with simulations from process-based models. And the fact the farm platform's been has had a rich history of development of process-based models and application because of its high resolution data sets. So process-based models, we can simulate crop and livestock performance, soil water status, nutrient budgets, emissions to air and water. They're ideal when data are scarce because they're scarce, because they require minimal data inputs, but they have multiple outputs. They're ideal from processes that are difficult to measure. Many processes on the farm are very, very difficult to measure. Sorry, the phone went. And they're good for forecasting decision making in the future, and they complement data-driven models. So you see in that schematic with the Venn diagrams, that's the in the past bit, that's the overlap between measurements and what a process-based model can hindcast or nowcast. There's actually quite a limited validation space of process-based models. And similarly, when we go forecasting in the future, which got to be informed by simulated weather and climate scenarios and what management you decide you want to do, want to investigate, there's again a minimal overlap between data-driven model forecasts and process-based model driven forecasts. So that's the coincidental forecasts. Here's a slide on the geographies of the farm platform. So you see the how the four free outdoor systems have evolved since 2010. We're due a new system change in next year, actually, not 2024, as it's said there. Most of our research has been done at the farm scale, but we can outscale from the farm platform, especially since if you look at this map here, over here you can see my mouse, we also monitor the catchment that the farm platform sits in, and that's got a more varied land use than the farm platform itself, and that enables us to outscale to about 40% of the UK. And we outscale informed by remote sensing data, national network surveys. So it's quite powerful in that way, even though it's three small farms in the middle of Devon, we are able to outscale, especially when we're monitoring the catchment too. So that's what we've been doing in essence. This is what we're embarking on a journey now, is to say, can we use the farm platform and this valuable data resource to start to develop a digital twin? This slide here, the difference between a digital model, a digital shadow, and a digital twin. Main thing, digital model, no interaction between the physical system and the digital system. A digital shadow, only a one-way interaction from the physical system to the digital system. And then a digital twin has this feedback loop. So you've got a physical system, you've got a sort of a digital twin of that system, but you inform back to the physical system, i.e. you make decisions and you enact on them. Or the other thing that is very useful, you can redesign the sampling and the monitoring campaign according to what the digital twin is saying. So a digital model, a digital shadow, and a digital twin all provide a decision support tool. A digital model is very common, which is a DST based on the digital model, which is a process-based one, is very commonplace. There's plenty of them around, whereas digital shadows and digital twins are more novel. We can answer what-if questions to inform decision-making for sustainable and resilient farming. Forecast accuracy and estimates of uncertainty. Estimates of uncertainty are very important, should improve with a digital shadow and a digital twin. And as I mentioned before, with the farm platform, its core remit is a monitoring platform, providing data for research. So we only view this digital twin of the farm platform is only a demonstrative farm platform. And we cannot implement all the decisions that the digital twin may say. Otherwise, it would compromise its overarching aim. The proposed analytical framework for our digital twin, we can have a digital twin for each of the 3 outdoor farms. So we're not going to look at the indoor farm yet. And we're going to couple process-based models are going to provide the core simulations, because we can simulate so much of the processes, which we can't do by measurements alone. One option is, because process-based models are made up of a number of component models, so we could replace a physics-based component model, say for soil moisture, in a process-based model with our data streams of soil moisture, which are a 15-minute resolution, so we could continue retrain a data-driven soil moisture model to improve soil moisture's rate, influences yield and gases emissions, so we can improve those forecasts by replacing the physics-based soil moisture in a process-based model with a data-driven model. So that's one option. And we can look at hybrids. Hybrids are very good when we want to look at sort of more detail, because really process-based models only tend to capture broad trends and patterns when forecasting. So here we could combine a process-based model with, say, an extreme value model, and to capture extremes better. And we've actually done that model already. The other one is to replace process-based models with the emulators. So we used data-driven models to emulate a process-based models, which are very good for reduced computational overheads. In our digital twin, I think we'll have a mixture of all 3 options. Here's just a mock-up of what a what-if dashboard would look like. So this is for the blue farm under 3 different management scenarios. So the top one up here on the left-hand side, so that's current status. We've got radar plots here. So we've got nitrate loss to water, phosphorus loss to water, calories, so that's the energy of the farm system, soil carbon, and carbon emissions. So that's the current status. We're going to look at scenarios for the same time next year. So we've got September 2024. What's the farm going to look like in a year's time, according to different management scenarios? So we've got 3 different scenarios there. And then with the digital twin, we update every 3 months. So this is an update of the current status for those 5 attributes. And then you can see how these scenarios will change as we update using the digital twin. So scenario 1 is slightly different, scenario 2 is slightly different, scenario 3 is slightly different. Again, for the same time, September in 2025. And then we can have another update. So this is now in spring 2025, and 6 months' time is what we expect the farm system to look like under those 3 scenarios. So that's just a mock-up of what a sustainability dashboard will look like, and one for resilience or net zero will look different. Quite a lot going on this slide. I'm near the end now. So this is the slide of what a modular framework of what our digital twins will look like. It's best to move from left to right. We've got the stakeholder platform, the data collection platform, which is already in operation, so we're lucky that way. Much of the data management is already done, so we're lucky that way too. Analytical toolbox, process-based model toolkit is quite good. We need to develop many of the rest. Then there are forecasting scenario streams. And then we've got the user interface, and then other, which I couldn't think of to categorize it better than other. And the colors relate to how they relate together. So like storage and processing, which is brown here, also relates to energy consumption efficiency. You know, we don't want to have a digital twin that requires so much energy it actually contributes to climate change. So that's that. And then last 3 slides. So this is the slide just on the data. The take-home from here is we've got 400 environmental sensors. We've got capacity to use remote sensing. The data sets in yellow are the data already goes straight to the cloud. The ones in grey have got the capacity to do so. And then we still get an awful lot of collection in the labs. So that's just the nature of things. And here is our demonstrator digital twin. It's got the feedback loop. So we've got the data here, moving to an information management framework. This is the digital twin. In this case, it was based on process-based models, or the emulation of process-based models using deep Gaussian processes. We'll have a Bayesian construct so we can quantify uncertainty well. And then we've got this going around here. We've got informed and timely decision making, so we can inform what best to do on the farm in the management situation. Also, we can feed back to the farm where, what, and when we should be monitoring. We could reduce some of our monitoring capacity or increase it. And that's the demonstrator farm digital twin. And the idea is to roll it out to real farms. And each farm could have a different level of instrumentation according to what level of digital twin they want. They could just have a basic digital twin that's just informed by remote sensing data, right up, and that's the basic standard, right up to gold standard, where they start to mimic what we got on the farm platform. And that's it. Quick share.
Great. Thank you, Harry. And we will, as we said, do questions at the end. And now Arjun will join us up here. So, sorry, whoever is doing the IT, we do need to get the local slides. Yeah, there we go. Great. Are these yours? Yeah. Or the next one? Perfect.
Hello, everyone. So our project is based on creating a large language model, using a large language model to create a chatbot for a major climate report. We started with the vision to create smart agents, which use LLM data agents and databases so that we can create a generic agent which should be able to answer information in a simple way to people regarding climate science and climate data. We thought it would, we visioned it to provide climate data and also help to perform certain simple form of data analysis and data exploration on the climate data. So we have a lot of complex climate data and climate models, and we want to provide that information to people who are not climate scientists so that they can use that information, summarize it, and use it for their particular work. So we decided to begin with using large language models to provide data and information to people. As a proof of concept, work on the Global Tipping Points report. So Global Tipping Points report was released by the University of Exeter's Global System Institute at COP28 on 6 December 2023. And we developed a chat-based interface powered by a large language model to summarize the information in the report and communicate that summarized information to people in a simple and understandable way so that it is well by the people who are not climate scientists. Our aims for developing the chatbot was to provide accurate information in the form of natural and answer information from natural language queries to people, to provide simple, summarize the entire information in a simple way. And our main focus was to establish a source of trust when using such large language models by providing sources from where the information was extracted and providing links to that extracted information so that people could directly go back to the report and read that information from the report itself. So firstly, we begin with the basics. What's the large language model? It is essentially an AI model which is based on a transformer neural network architecture. It is capable of answering queries in given in a human-like way and answering it in a simple and summarized format. What is a chatbot? So in our case, we have encapsulated the large language model, we have encapsulated the source Global Tipping Points report, and we have established a retrieval augmented generation mechanism in the entire system we call as a chatbot, so that given a query, this entire system will understand the query and give you a summarized and a simple response. What is retrieval augmented generation? Well, it's a method of extracting information from a source database based on a given query. So if you have a given query and a database, it will extract that information that belongs to the part of retrieval. It will augment that information from other sources, and then it will provide it to a model that will generate summarized information from that source of information and answer it in an understandable way to an audience. This in front of you is a prompt. A prompt is an instruction you provide to a large language model to generate information. It's quite understandable in the way that you are exactly communicating with an AI model in a human-like way. So something that you'll speak to your friend to ask your friend for a certain amount of information, that same way you can speak to an AI model. So here I'm asking the model to provide information using only the Global Tipping Points report. I'm asking it not to provide information from any other sources. And I'm even telling it that this information will be reviewed. Hence, please do not deviate, as it may create problems in the evaluation. So things that you normally speak to a person, you are communicating it to an AI model. So it tells the chatbot to behave in a certain way. It tells the chatbot not to deviate from a certain way. And it tells the chatbot to return that information in a particular format. This is the entire framework of the chatbot. So we have two steps here. So first things, you have the pre-processing of the source information, that is the report. And the second thing is you have pre-processing of the query. So you have the entire, so I'll explain it one at a time. So the large language model used in this case is the GPT 3.5 API. And the entire thing was deployed to cloud. So first step, we are pre-processing the Global Tipping Points report. So we are taking that information and we are dividing that information into small pieces of information or chunks. Why? Because a model cannot read 100 pages of information at the same time. It's too much for the model, so for better processing, we divide it into different chunks. Each chunk or each part consists of 1,000 characters each. So it's a small piece of information. We then take each part and convert it into a numerical representation known as a vector embedding. So we convert it from a character space to a vector space. And we store it in a database where we have a chunk, we have its numerical representation, and we also have the source from where it is extracted. We then perform pre-processing on a question. So given a question, we design a prompt for the large language model to understand what kind of a question it is. So humans can formulate questions in different ways. And it becomes difficult to understand what is that question asking for. Is it asking for questions from a report that requires only text-based answers? Or is it asking for images? For example, if I make a question like, what does the Global Tipping Points report tell me about tipping points in the Antarctic? So do I only want a text-based answer directly from the report, or do I want to see illustrations with it? And to make it's very simple for a human brain to understand that information is not simple for a automated system to understand it. And that's where we, again, use a large language model to divide it. This is the prompt which helps to divide that. So we take a question and we tell the large language model again that you have a question. Now tell me if it's asking for something from a textual database, or is it asking for something of a visual representation? So if you have a question like, show me all the graphs in the report which correspond to cryospheric tipping points. I'm asking for images or graphs, and then the response would be, the image part would be, the user question is asking for graphs, and the text part would be, there is no reference to any textual answers which is required. Finally, we take the sources of information. So once we have the question, we convert that question into a numerical representation, and we find semantic similarity between the numerical representation of the question to the numerical representation of our source information. This is done with the help of cosine distance. Once we get the cosine distance, we apply filters to it. We say that remove all irrelevant questions which is less than 70% relevant. And why this 70%? It's not something that is established in previous research. It is something that we have experimented on continuously to establish the threshold of 70%. So anything below 70% of similarity, it's basically information which is not relevant to the question. We also try to establish a balance between relevance and diversity. So given our 5 pieces of information, they should be different from each other, and they should be very much relevant to the question. We collect that information, and we provide it to the large language model, and we provide it with a prompt, and the large language model summarizes that information to create an answer. This is what the user interface looks like. You have a question. For that question, you have a text-based answer and an image-based answer. We do have sources. So for every answer, you have sources, which is a hyperlink. So when you click it, you can exactly see what information and what chapter of the report, as well as what relevance it has to the question. We also established a feedback button. So this was present in our user testing, and we said, why not provide it to people who are attending COP28 to get their experiences on what they felt while testing out the chatbot. And if they felt that some information is irrelevant or some information is generic, they can provide us feedback, and we can say, OK, what went wrong? Let's see. This is the demo. I'll show you. Will probably open up. So here, I'm asking it a very sample question, and you'll see exactly how it works. So given a question, it'll perform the processing. And yes, so you'll get questions, you'll get the text-based answer along with the, oh wait, is it not sure? Yeah, so given a question, you can see the text-based response as well as the image-based response. And when you scroll down, you can also see the sources from which it has extracted their information. Yeah. Okay. So we decided to test this chatbot, and for the COP20, for our demonstration, we performed user testing in 2 groups. The first group consisted of, we decided to test the chatbot in 2 groups. The group 1 consisted of authors who formulated the report, and we tested to see if the report was spreading incorrect information or missing information or not. And then we decided to give it to a second group of people who consisted of postgraduate students at the Global System Institute at the university to get their feedback on the performance of the chatbot. The results of the feedback showed that the chatbot did not spread any potentially harmful or incorrect information. However, some of the user testing sessions also showed that some of the answers provided were generic a bit and may have missed 1 or 2 facts which would have improved the performance of the answers. So, based on this, the feedback collected from the tipping points report, we started working on a new project, which is currently ongoing work called the UKCP Climate Chatbot. So UKCP is United Kingdom Climate Projections. It's a dashboard which contains climate projections, climate observations from climate models all over the world. This project is currently in beta phase of testing. Our target functionality is to, given a query, we want to extend the functionality of the global tipping points chatbot. We want to provide answers in the form of text and images. We want to provide it the ability to extract information in the form of UKCP climate data. And we also wanted to give the ability to perform data analysis, that is, extract information like what is the mean of my data, or what is the climate trends between in range of interval of years. And we want to plot that data just by communicating it in a very human-like way. We have another presentation, another PowerPoint slide, which I'll try and present. Yeah. So this is the demonstration of the UKCP chatbot. So first, I'm trying to extract data in Liverpool. It'll ask me what resolution do you want the data as, and then it will ask me some of the details. So I can communicate with it in any way I want. It will understand what I'm trying to say. It will collect the parameters of the query. It will make a query response. It will query UKCP and will provide me the data. So as we go down, you will see a download button. Yeah, so you can download your data now. You can even ask what is the mean temperature in a particular year. It will calculate and show you. And finally, you can also ask what is, and just ask a generic question. It will give you a question with text and images. And this time, we have improved the image-based functionality. We're not providing a single image. We're providing a range of images, because extracting images to what the user wants becomes difficult, because semantic similarity does not capture the entire thing well. So we are providing a range of images so that we can understand what the user actually wants. Finally, just let me change it. Yeah. Yes. So we now want to discuss a few things with you, that is trust and accuracy. We know large language models are susceptible to hallucinations, and large language models can spread information which to a person who is not a climate scientist will be absolutely correct, but it is not factually correct. We handled it to a certain extent. We gave the sources of information to track it directly to the report. We provided several filters on similarity so that we can remove irrelevant content which the LLM has used. And we also provided the feedback button to see if incorrect information was being spread. But this is an ongoing research topic. Hallucination has not been removed yet, and we are open to suggestions on about things related to trust and large language models. Finally, we also wanted to discuss testing and validation. Testing and validation of such models where you do not have quantitative testing metrics becomes difficult. We believe in human in the loop when it comes to AI, and therefore we always, in the Global Tipping Points report chatbot, we always use human-based testing sessions. But this time, we are focusing on something different. We are creating 2-phase testing methods. We want to evaluate something something called quantitative testing of text-based information using precision and accuracy metrics. We want to decide on a set of parameters that provide those best metrics and then provide it to human-based user testing sessions so that we can improve on our methods. Thank you for your time. Yeah.
Really interesting. Hello. Really interesting, and as someone who writes such reports and tries to communicate them, I'm really interested in the idea of being replaced. And I think, no, in a good way. I mean, so I guess my interest is in uncertainty. So you partly answered how it communicates uncertainty in the report, because for the sea-level information it was providing different scenarios. So I'd be interested to hear, like, to what extent does it communicate uncertainty in the report? To what extent can it or does it communicate its own uncertainty? And thirdly, are you planning to use uncertainty in the user assessments of accuracy? Because I think that would vary according to who you asked, their expertise level, and also which audience it is being communicated.
So, firstly, I'll answer the first part of the question that is related to uncertainty given by the sources. So what we do is we find similarity between the source of information and the question, and if the similarity score is to a good high extent, then we establish uncertainty or confidence in that particular source as a potential answer. And when it comes to user testing, we are trying to create different user groups. So first user group will have a level of expertise, that is, they'll be climate scientists at the Met Office. Second user group will have a lower level of expertise, that is, they'll be postgraduate students or PhD students at the University of Exeter, most probably. And third, it will just be undergraduate students and general interest public who are interested in such work and they want to evaluate the chatbot. And then we'll collect the metrics, and we are deciding on certain measures like accuracy to the answer, relevance to the answer, how simple is it to evaluate the answer, and we want to see how the model performs in each level of expertise. Our initial expectations is with user group 1, who are climate scientists, we are expecting that the accuracy values will be relatively low compared to the user group 3, which uses the public to provide feedback on the answers. And we are trying to focus, our main focus will be to increase accuracy for the user group 1 as much as possible, using different methods of improving performance. Because if user group 1 is satisfied, user group 3 will also be satisfied, because they will know what is correct or incorrect in a particular answer.
Although, can I just suggest that you have the experts also assess the other groups, because the kinds of simplifications you make for a public audience can be better or worse as assessed by the experts.
Okay, yeah, sure.
Do we also have Isabelle online? Okay, maybe not. So I will jump down to a question for Paul then. Also, Harry is, we should call you Harry, correct? Yes, Harry. So what do you see as the key benefits of agricultural digital twins for future focused planning?
The main, you get decision support tools in agriculture already that can help inform on decision making. What's the best management practice to do given a certain climate scenario or weather scenario? Digital twins will just enable more timely updating of those scenarios, and also capture uncertainty better, because they'll have a data-driven component rather than a purely physics-based component. So that's the main thing, as I can see. And as farms become, if the digital twins are shown to benefit farming, then more farms will take up the initiatives and put sensors on their farms. Farms are currently putting sensors on their farms. Soil moisture sensors are quite simple. The biggest challenge is that many processes that we need to capture can't be measured very well. The sensors don't exist.
Thank you for that answer. Sorry, it's a bit awkward to with someone on Zoom to tell when you're finished. I didn't want to cut you off. Do we have anyone else in the room? And keep in mind, I don't believe we have Isabelle online right now, so I'm going to save questions for her.
Yeah, for your talk, was you have the chunks. Was your embedding some standard embedding technique that had been trained on general corpora, or did you either learn or fine-tune it to climate literature corpora?
For the global tipping points report, we didn't use fine-tuned embeddings. We use OpenAI's trained embeddings or text embeddings adaptive 002. And for the UKCP report, we took a language embedding model. We trained it on question-answer pairs. So we created synthetic questions. We created answers of the synthetic questions solved derived from the report. And we provided those question-answer pairs to the embedding model so that it learned about the domain-specific information and the semantic space of that information. And we currently have a non-fine-tuned model and a fine-tuned model as parameters, and we are testing to see which performs better.
Great.
Hi, again for you. So half of the question was asked for Claire, but the second part of the question was, which kind of LLM are you using? And did you see that if you use many of them, did you see that when you use the RAG, they start to perform as similar, or if you see any difference between them?
Again, for the global tipping points report, we stuck to GPT 3.5 by OpenAI. For the UKCP, we are comparing between Llama 2, GPT 3.5, GPT 4, and the new Google LLM called Bard. And regarding RAG, the RAG that we use for the global tipping points report was a very simple one. But for the UKCP report, we are using a completely new way. We are permutating questions in different languages and in using different types of ways to create different versions of the same question. We're establishing similarity for each of these questions using fine-tuned models. Then we are taking that source of information. We are providing it to a small to big algorithm that uses that small piece of information to go to the big version of the report and get more context from the big version of the report. We're combining all that information in a new RAG framework and providing answers. So for the same large language model using two different RAGs, that is the basic one for the global tipping points report and the new one for the UKCP one, the new RAG approach works much better. However, we still are working on comparing the different large language models, but before that we are working on a new framework, that is instruction fine-tuning a large language model, because we know that when you instruction fine-tune something, it gets rid of its external information. So the LLM will no longer use leak information from Wikipedia into one of its answers. It will just use the source information that it has. And our aim for doing so is, again, establishing trust in our model, because we do not want anything other than what is present in the report to be present in our answers.
Okay, so but for now you don't know if, let's say,
no,
Llama
so we are still in the process of testing.
Okay, thank you.
Okay, so unfortunately it looks like we won't have Isabelle back, so if anyone has questions for her, please hold the questions, but go to the Slack channel and find her there. And then she should be able to also look at Slido, so hopefully there's still a chance to ask some questions and interact. I'll go back to Harry. Is your digital twin research linked to supply chain modeling of climate effects on food production? And if there is such work underway, does data availability affect that?
We've always tried to link the farm platform to supply chain, but it doesn't really. We don't capture enough information. There has been work on life cycle assessment, but essentially no, we can't couple it that way very easily. We do get data from the abattoir, so there's a supply chain there, but it's limited our supply chain influence,
Okay.
in essence.
So basically, the second part of that question, does data availability affect it, is yes, very much, it sounds like. And so kind of on a similar vein, what is the gap in the modeling capacity for the planned farm-scale digital twin?
So we're quite good with process-based models, and we do need to have the source code available. So there's quite a lot of process-based models that are closed. So we have trouble there. Data-driven models, they're all fine. I think, really it's gaps in the data. Gaps in the sensing technology that's more than gaps in the models. But we do have trouble with some process-based models being closed. We only have the executables. They also operate at different spatial and temporal scales, which is also a challenge, especially if we want to put them in an ensemble.
Thanks. Anyone else in the room?
Thank you. Another question for Harry, if that's all right. So you've got all of these sensors around these farms. How do you ensure that the quality of the data that you're getting is reasonable? So do you detect the drift in certain degradation of sensors or skew, that sort of thing?
Yeah, because we've been making it open for a number of years, we've had to do that anyway. So they've all got a basic. So the data that we release has got a basic level of quality control. But as part of the digital twin, we're going to do more advanced quality control on those data streams, including different options for infilling and different options for anomaly detection and so forth. But yeah, we do all those drift corrections as part of releasing the open data anyway.
Thank you.
So we're ahead of the game there, really. It's useful.
Okay, we have 2 minutes left, so I think I'll go back to some questions about LLMs, try to summarize maybe a couple of the Slido questions together. People are asking kind of about the challenges of LLMs. You addressed the issue of trust, but one question is, well, someone's suggesting that Queen Mary's are doing a lot of work on the challenges regarding linguistics, and wondering if maybe you've seen that or worked with anyone from there, and maybe they could help frame the questions and the metrics. And then the other ones I was going to bring in is, do you think that the LLMs could help researchers in exploratory data analysis?
Yes, that is something that we are currently working on. The challenge is to make sure that the LLM is answering correctly. So the data that you saw, the mean, before this presentation, we actually pre-processed the data in a spreadsheet and we've calculated the mean and we compared to that answer. So that is one challenge for doing it, but our vision remains to use it to not only get statistics on the data, but also different kind of plots, correlation plots, uncertainty plots, things like that when it comes to handling climate data.
Great, thank you. Well, I think, any last questions in the room before lunchtime, or are we all too hungry for questions? Okay, great. Well, thanks everybody. Let's wrap it up.
So this session is going to be 3 talks, each 15 minutes, and then we'll welcome back our speakers, like this morning, to the front and have a 20-minute Q&A. Yeah, so save your questions until the end. And also, don't leave too quickly because we'll have a group photo at the end of this session. So stay in your seats at the end of the talks. Yeah, so let's get going. We'll start with Peter Meers from the Helmholtz Center for Environmental Research. Thank you.
Yes,